Hi guys. So I'm supposed to talk about TensorFlow, and that's a big subject now. So since we have 2 hours, that's a lot of time. So I think this will be mostly driven by you. I mean, I need to know what kind of things you really want and need, because TensorFlow is a very generic programming model, and it's also a whole ecosystem around it nowadays. So I'd like to know, first of all, what do you know about TensorFlow? So who has used TensorFlow? Okay, so half. So what's your interest? What would you like to do? Or
I mean, the fundamental of TensorFlow, why do you use it and where do you use it? I mean,
right, so let me start with a bit of history and reasoning why it came to be. So there was a first generation machine learning system at Google. It was called Disbelief, and it exists, well, it was used for speech recognition and a number of projects. And it was similar to what Torch is nowadays. So it was a system where you would define objects that were layers, and they would have a forward function and a backward function. And that's how a lot of people think about machine learning. And it was used in Google infrastructure. And the problem is that if you have a system like that, something new comes up, and deep learning is a very active field. Something new comes up every week nowadays. Something new and bigger every month, maybe. And you need to write a new layer. And in Disbelief, the new layer you'd have to write in C++. It is okay for one layer and another layer, except some new things, they go away. Someone needs to maintain this layer. No, the code degrades, you change something in the framework, doesn't work. And this came to be in the same time as GPUs came to the stage. And what you have to realize is now you have to rewrite every single layer in a code that's compatible with CUDA to make it run on GPU. By that time, you have 5,000 layers, which you need to maintain in 3 versions of the code. And you're starting to think that this is not the best design. So TensorFlow came to be to correct this problem. So how do you correct a problem like that? It's a generic problem that you might have in any system framework, in any programming language. And the solution that we use for programming is we have compilers, right? You need a different assembly code for ARM. You need a different code for Intel. You might do different, but you just write things in a programming language, and the compiler does the work for you. So the idea for TensorFlow is that instead of having these layer objects that are big and you have a lot of them and you need to maintain them, you have very small ops. And these operations, you build a computation graph from them. They're like primitives, like adding, multiplying, maybe matrix multiplies. You build a graph from them, and then the only thing you need to maintain are implementations for these ops, which are maybe not that many. Addition, multiplication, of course, now they've grown a little bit, but it's still way less than the number of compound layers. So you only implement these ops, and that's it. That's what TensorFlow does for you. It provides you a set of operations, very basic, and the ability to build graphs from them, and you're on your own. That's the core. But now that doesn't really allow you to make a neural network. Because a neural network has these things like gradients, backpropagation, training, optimizers, and a lot of this. So now you need to express all of that on top of this very basic framework. And how do you do this? Well, you need to have helper functions that will build subgraphs composed of these ops and put them in the right place in your computation graph. For example, maybe you just wrote a function that's a forward pass of a network, and you need something that will look at this graph and build you a backward pass, so you don't need to differentiate on your own. So you have auto-differentiation by going over the graph and building a backwards pass. maybe you need an optimizer that will update some variables, and how does this fit into this ops and graphs model? So the reason for TensorFlow was to make it possible to maintain a large-scale machine learning system primarily designed for machine learning, but it can be used for any computation, any numerical computation on the large scale. But what you see from this is that it's a very low-level system, right? You have the ops, and you have a graph of them, and they will execute. That's the core tensor. That's the very low level of TensorFlow. But of course, on top of that, things started to appear, like helpers to build new layers, because people don't want to write the smallest ops every time. So it became like a whole ecosystem from the part that you have these ops, and now they need to run on very different pieces of hardware, because currently TensorFlow will run on CPU, on GPU, but it will run on your phone on ARM architecture CPUs and on special coprocessor that Qualcomm developed to speed things up, on the Apple coprocessor, hopefully soon, on the TPU, which is a Google hardware, on Intel Nirvana hardware. So there's now a lot of hardwares which are like targets for this compiler, but you only need to rewrite the ops for that. So that's the low level. And then there is the higher level. How do you make optimizers and like layers from these ops? And then there is the even higher level, like how do you organize these layers into frameworks like Keras and so on. So what we're talking about is a very multi-layer system, which is quite similar to a programming language, right? You have the compilers that produce the assembly and it runs on the hardware. And then you have the basic libraries, and then you have the higher level libraries. So that's why it's hard to say what is TensorFlow in general. Well, it's this multi-layer system that helps you, and it's also distributed. So it also, from the scratch, made to run on multiple machines. So there is a lot to it. And which part of it you're really interested in depends on what you're doing a little bit. That's why it might be hard to go over everything, and maybe we can spend some time to just tell you the parts you're really interested in. Let me start and give you the overview of the core model, and then we can move on to So the core TensorFlow computation model, as I said, is a graph of ops and their execution. So people call this a data flow system. So you have these nodes, which are also called ops, and the arrows, that's where the tensors flow, right? Between every two ops, what flows there is a tensor. A tensor is like a multi-dimensional matrix. It has a type. It can be integers, floating points, even booleans. And we make a graph of those. And this graph will be executed. So that's the most basic idea with tensors, right? So the things that flow here, in some computing systems, they are just variables or constants. Here they are matrices, so they can be very large. And so that would be all fine, except we also need state. Because in neural networks, you have these weights, and you want to update the weights. So you need some state here, and this is a variable, it's a rectangle. And some ops are allowed to update other ops. Okay, so some of these edges are actually dependencies, and they say, oh, this op should be updated with the result of this. So for example, we have the assign add op that has these two dependencies, and it says, well, once you've computed this, please update that thing to be a sum or a difference of this and its previous value. So now, why the state is a little bit tricky is that this system is distributed. So these ops, they don't have to be on the same machine, and they're executing all in parallel. There is no inherent order other than the order given by the edges. So with TensorFlow, every op, you say, oh, I want this op on machine 7 on GPU 1, and I want this op on machine 3 on CPU. And you tell it, and TensorFlow will put it there, and it will start executing, and the moment when there is something cross-machine, it will add special send and receive nodes to make a transfer through the network. And this is totally parallel, like you don't see this. The send and receive ops, they will get added, things will flow, and it will execute.
And how do you manage the concurrency here? I mean, for example, if one machine is trying to read and the other one is trying to write it.
There are no mutexes, there are no locks. Everything happens asynchronously. So you're on your own. You are allowed to add dependency edges. So you can see this op should execute before this op. And then it will be, the order will be retained. But other than that, it's just running. The way it actually happens, schedules the ops on every machine and starts executing them. From the ones, no, this op has a dependency on this, right? So this has a dependency on this. So it will first, of course, execute the ops that have no dependencies, then the next, and so on. But it's a distributed system that's very asynchronous. So if you're not careful, you'll start updating things in a very strange order. But in most cases, in deep learning, it doesn't matter that much. You're just adding gradients. It doesn't matter when you add them. But if you're using it for other things than deep learning, you have to be very careful. OK, so what's not in the core model? As you see, there is no mention of neural networks there. There is no backpropagation. There is no gradient. And when it comes to the distributed thing, people used to have things like parameter servers and workers. So the parameter would be distributed. They'll be sending everywhere. There is nothing about this in the core model. The core TensorFlow is a bunch of ops. Some have state, and they can be distributed and send things in between. It's just that, and everything above is for higher level libraries to do. Now, the big advantage of making a division like that is that when you're implementing a new hardware, you've built your Intel, you've built a new great hardware for machine learning, you've built a new set of operations for your processor, you only care about this, right? You only need to make sure that the implementations of this bunch of ops, adding, multiplying, maybe there is some special softmax op, you need to make sure that that runs fast on your hardware, but you don't care about all of this. You don't care about gradients, you don't care about differentiation, right? That's the benefit of the design of this system. You make a split between who cares about what. OK, so, but now we need to implement gradients somehow and do training, right? How do you get from this low level to a neural network? So, so there are two things. First of all is how do we assemble large graphs of operations? And the second thing is how does this graph actually execute? And so this is where most of the work goes. And this is not so hard, but also some work. So the basic thing is there is something called a session, and you run it. And we'll come back to it. So let's think about graph construction first. So early in TensorFlow life, there was this decision made that we'll focus on Python. So you could construct graph in any programming language, but the idea was we'll make functions to build graphs in Python. And so how do we build a graph? We have constants, variables, operations like plus and minus. So you just write tf constant, TF variable, and then you overload the plus operator on this TF objects, and they construct a plus node inside the graph. Okay? So what's a constant? Well, just say A equals constant or TF constant. You can construct them from NumPy arrays as well, of course. And that's it. Variables are like constants, but they hold state. So they can be updated. Right, this is a question that many people have. So when you're a TensorFlow user, you'll usually say TF get variable, and it will give you a variable node, and it can take an initializer argument. When you start running, this variable will, in the first time, get randomly initialized to something, but in the next time, it will be loaded from a checkpoint. So the question is, how does this thing happen in this model where you just have nodes and graphs, right? How does initialization work? So the way it works is actually like this. You have this variable thing which has a state. You have an op that gives you random numbers, like random normal distribution. And you have this assignment op. So when you say TF get variable, it constructs all these ops. And this assign op, it will assign something to this variable. And then, in another place, we construct the op that reads from a checkpoint file. So it actually checks whether a file exists on disk. And if it does, it will overwrite this random assignment with something that's on disk. And you need to be careful. If you do it in the wrong order, you can overwrite your variables with random stuff. But luckily, the higher order things will do it for you. Okay, so what ops do we have? We have these constants, we have these variables, then we have add, matmul, things like this, and they're overloaded with Python operators, right? So when you write something like this in your Python, what actually happens is there is a default graph, which when you say import TensorFlow, it's there. Writing this adds the node to this default graph. Writing plus overloads this and adds another node, which is the add. And in the end, you're holding on to the y, which is this node here. So what ops do we have? We have array operations, concatenating, slicing, reshaping. We have mathematical operations, ReLUs, convolutions, pooling. And nowadays, we have a large number of various operations. But, well, this number may be large, but it's still, like, there is a web page that indexes all of them. And a lot of them are quite simple, right? So it's not like every layer has its own op.
So if I am a hardware producer, like NVIDIA, I have to support all those
ops, yes. Okay. Yes, you have to support all the ops. Well, but a lot of ops are I/O ops, like disk reading and so on. Okay. They only happen on CPU. You don't need to write support for them. So mostly you need to support the mathematical ops and some of the ops like convolutions.
But can one be defined as like a metaphor? Like there is.
Yes, we define a lot of ops are defined in terms of other ops, but we'll come to them. And some ops can also have variables. So we'll come to defining your own ops and layers in a moment. But then there's still a few things to go. like one thing is the gradient. So we have a graph, we have one variable, another, many ops that do something on them. We have a loss, and so what? So this is a forward pass. How do we get a backward pass of the neural network? Well, you call a function that's called TF gradients. It takes the loss, scans the graph, and builds gradients for all these variables. So how does TF gradient work? Well, the way a chain rule works for differentiation. It traverses the graph backwards, it knows the list of variables, and it constructs the graph that would calculate gradients. What do you need to know to do that? Well, for every op, you need to register a function saying what's the gradient of this op. And TensorFlow has a mechanism to register it. So you annotate the op with the register gradient annotator, which says what other ops are used to compute the gradient. And some ops don't have gradients, so this process might fail and raise a warning or something. But most of the ops where it makes sense have that. Okay, here is some example, but maybe we don't need to go into it. Okay, so gradients are one thing, and then you need to update the variables. So you have a variable, you have the gradient and the learning rate, and the simplest optimizer, which is the pure SGD, it's just this subgraph. It has the variable, it has the gradients, and a tensor that's the constant with the learning rate. It multiplies the gradients by the constant, and there is a node called assign sub, which assigns to this node the difference between this and this. But, of course, so this is the basic optimizer, but there are a lot of optimizers, right? There are some in the core TensorFlow with Adagrad, Momentum, Adam. So you need to have some variable for the running average of previous gradients and the square root of their variance and so on. But they all do it for you, and it's easy to add your own optimizer. And people are adding a lot. So now, how do we train a neural network? We built this graph with ops. We have...
This optimization is distributed also, or is distributed the optimization of the neural network?
So what the optimizer does is create this subgraph. It doesn't know it doesn't change anything from the core TensorFlow model. So all nodes of this subgraph can be distributed because the core model is distributed. So for example, if this variable is on one machine, then the gradient function, it usually collocates the gradient nodes with it tries to put the update nodes on the same machine as the variable. And it can also try to put the ops it's computing on the same machine as the ops that led to them. Right? Because to compute a gradient of an operation, you usually need the things that were coming into it. So it's best to try to put it on the same machine. And yeah, so it's very distributed, but just by the virtue of TensorFlow being distributed on its own.
The assigned sub is a simple subtraction. Is it the simple?
Yes. Well, no, well, it's an op that will, but this is a stateful node, so it will modify the state. So it's simple, but it acts on something that has a state. No, because most of the ops, like minus, they create a new tensor. It's not a permanent state. Okay, so here is like a very early MNIST graph that looked like there was some input. And models usually have a variable that's called global step. It's a stateful variable that tells which step of the training are we in. And well, the inputs, you maybe need to reshape it, have a ReLU layer, have some logits. there is a cross entropy op. You sum, add, put it into this SGD, and that's a graph. It's an early example. I think it looks a little bit different now. But so we have our distributed graph. We built the graph. How do we run it? So there is this session API where you say, OK, run a graph. But what does this mean? The graph has a lot of nodes. Some of them are constant. Some of them are variables. Some of them are maybe not needed. What part of the graph should it run? And some might depend on things in things somewhere else. So you have your Python program that's created the graph. The Python program creates a session thing that calls the runtime, which is actually in C. And it will run ops on CPU and GPU. So that's how it looks on your one machine. Now, with more machine, you still have your Python program. It will still create graph and call the session run. Except now, there is a master machine, which can actually nowadays be the same as any other machine. It will distribute the graph to many machines. And these machines, they don't actually need to be running your Python binary. They can run a generic TensorFlow server, because the only thing they'll be doing will be executing ops on these things. And they'll be communicating through the network with these sends and receives. And they're still just running your graph. So you can only think about your graph as running on multiple machines, but there is something to be done to actually start them up, right? So you need to start a TensorFlow server on all these workers. You need to send your session to the master. And this is usually done by higher level things like coordinator and managed session nowadays. But it's good to keep in mind that there is something like this happening in the background. So in the session creation in Python, you specify what kind of session is it. Is it a local session? Is it a distributed session? And, oh, right. So you have the graph. You run the session. So what does actually run? And the session has like constant nodes. They can run every time. But what do you want to get from the graph? So you should specify what we call a fetch, meaning I want the value of this node at the end. And usually, the node you have at the end is a training op node. So you'll actually get a node that does nothing, but it updates the states of your variables. You might want the training op and the loss. But it's a very nice feature of TensorFlow that you can also fetch any other node from the graph. So you can tell, well, in this step, I don't want to train my model. I just want to see what would be the output of the 7th node of the second layer on my current inputs. So you just say, please fetch me this. And it's an argument to session run. You just say, this tensor. Because many people ask, oh, how do I get the output of a third layer in TensorFlow? Well, it's very simple. You just specify, please fetch me this thing. And that's very deep in the core TensorFlow model. You can fetch any op from the TensorFlow graph. So if you decide to fetch this op, you don't need to run these two. That's why the TensorFlow session actually does some work in the beginning. It checks all nodes you want to fetch, and it prunes the graph after them. So you'll only be computing the things that you need. And this is a little tricky because normally in programming languages, people have either a lazy execution model or an eager model. In an eager model, which is what most programming languages have, you start at the beginning, just execute things. Everything gets run. In the lazy model, you start at the end. It's like Haskell has this model. You say, oh, to compute this, I will need to compute this and this. Let me try. So you'll ever only execute the things that you need. In TensorFlow, it's a mixed model. You have a single pass backward from your fetches, which prunes parts of the graph. But after this, you have an eager execution from the back. And this has some unintended consequences if you have conditionals. So TensorFlow does have conditional nodes, which are called tfcond. The problem with these conditional nodes is that when you have a fetch, you don't know which branch the condition will take. So you cannot prune one of them. You have to keep both branches. Now, if you're not careful, you might get both branches executed. That's why to make a conditional in TensorFlow, you need to use lambdas for the branches. And you need to be very careful to enclose the whole subgraph of the branch in the lambda. Otherwise, it will execute both things and just discard one of them. Randomly? No, depending on the condition. It's like an if something, if I bigger than 0, then this, else this.
So it's a matter of speed performance.
It's a matter of performance. It will be correct. Okay. The problem is it will run both things. Because in a distributed environment, it's not clear what to do, right? Should you wait for the conditional to run the branch? Should you not? It's a bit unfortunate choice for conditionals, but the choice was made, like the whole design was made for machine learning, where conditionals were at that time quite rare. They're still, like, they happen, but they're not so widely used. It's not like a normal programming language where everything has an if. But it's good to keep in mind that it's a little bit of a strange model. You specify the fetches, the graph gets pruned, but the conditional branches cannot be pruned yet, and then it really executes everything in an asynchronous fashion going upward. Right, so here is the pruning. And then, right, and as you specify fetches, you can also specify feeds. So for example, maybe you just want to experiment and say, oh, if instead of this node that I'm reading from disk, I took an input that's exactly that. You can do this. To every node in your graph, you can put a value, and it will run with this overridden value. So you can override everything in your graph. You can also have nodes that we call placeholders that need to be specified a value. Question? No. So this is something in the very core model that allows you every node can be feed and fetched and will be run.
Input are placeholders, or they're only for the placeholder are only for debugging?
You can use placeholders for input, but in most cases you would like to read input from disk, and then we have ops that read from disk. They are parsing ops that will open a file and read. We call them TF examples. It's a format for reading. The advantage is that you don't need to copy from memory. Like, you don't need to construct things in Python and NumPy. You can very quickly read them from disk. And especially in a distributed environment, it's much faster than trying to make a process to feed. OK, so that was the core. That's how the core TensorFlow looks. That was the basic design. Mm-hmm.
But if there is an I/O in a distributed environment, it means that all the nodes supposed to have that local files in the all nodes.
So TensorFlow was designed at Google, and Google has a global file system. So there isn't really a notion of local files that much. You have a path, and in our file system, the path must be accessible. If not, it will raise the file not found mistake. Now that causes some problem to people that run on Amazon and like start 3 machines, but only 1 machine can read because the file is not accessible to other. But I think you can have a distributed file system on Amazon as well. But you need to set it up. And depending on where you are, it might be easier or harder. But right, so that's the basic thing. And now, as you see, this has some amount of complexity that doesn't make writing networks as pleasant as, okay, convolution, softmax, please train me my image recognition model. But please keep in mind that TensorFlow was the second version of Google internal machine learning system, and the first had these nice things, and it turned out to be unmaintainable at scale. So all this complexity is there for a good reason. The reason being that we want to run on 10 different hardware platforms in a distributed manner. And so, yeah, when the next time you see like a page-long debug message, like the TensorFlow team is trying to actively work on hiding this complexity behind more higher level things. But it's there, and you can debug through it, which helps people find mistakes and performance problems. Okay, so higher level API. So I split the higher level API into a bunch of things. So there is the higher level API that's very much in the core TensorFlow, that are like the easy helpers, like a standard library in a programming language. And then there is the higher level API that's either in Contrib or outside of TensorFlow, which are libraries like Keras and, well, Keras is now in core, but these are libraries that's on top of these things, make it even easier to build networks. So this is the more like the standard library. There are training utilities. So when you train a network, what do you need to do? Well, you need to have your loss and a training op that updates the variables, which is given by an optimizer. You need to execute this op, but then every so often you want to save the state of the variables on disk, because maybe you'll stop training or your machine will crash or something. So you need these checkpointing restoring ops. Then, if your training is taking a bit longer, like hours or days, it would be nice to see what's going on. How is the loss changing? Maybe you want other things, and there is this tool called TensorBoard, which will make beautiful graphs, but you need to put in the model some ops, which we call summary ops, which will save these things to the event files. And then there are other things, like, for example, maybe you want to check for not a number infinities in your floats and so on. So it would be nice to add these things automatically, right? You don't have to remember every time you write a model to check for numerics and things like that. Right, and then there is another thing which is recently changing, which is how do you read the inputs? Because, well, we said we'll read from file, but this reading from file was and currently is in many models done with Python queues. So you'll have a queue that's actually based on Python threads. And that turned out later to be a little bit of a poor choice. So there is a new API, which is called tf-contrib dataset, which has the queuing of the input actually done inside TensorFlow graph, in multi-threaded on the C level. So I think that might be worth mentioning, because you need to understand, like, the prime thing people experience as their first problem in deep learning is they come in, they download the data set, some images, let's say, they write their small model, they run it, and it's slow. I mean, after a few bugs, it starts running, and it's extremely slow. And then you say, oh, what did I do wrong in my model? And then you try to debug. The problem is the model is totally fine. What's very slow is the input. Because you need to load, images are not that small. You need to load a batch of them to be processed. And I mean, it might work for MNIST, okay, but if you go to larger images, you need to load a batch of them, and they're in JPEG. So first of all, you need to decode all of these images. So now a modern neural network on ImageNet can get up to like 2,000 images per second in processing speed. Now, you cannot decode 2,000 JPEGs a second when they're 300 by 300. So you can decode maybe 30 JPEGs per second. So you're 100 times slower than you should be because all your machine is doing is trying to decode JPEGs on CPU. Now, one very good thing is to not do this in a single thread, because most modern CPUs, they're multi-threaded, and they can at least run 10 of these threads in parallel. So that was the idea behind the first multi-threading thing, but that happened in Python, and Python has a lot of quirks with thread. It has a global lock for them and so on. So this was running, but had a number of problems, and also you needed to specify the number of threads and things like that. So now there is a newer API that runs on the C side and does this a little bit better, but it's still in development. So see, this this input reading is a hard thing. But one thing to remember, if your model is slow, check how fast your input is. And especially if you want to work with images or videos. Okay, so now, assuming you got your input, you want to write your model, and let's say, well, if it's a text model, it will be an embedding. If it's an image model, you might want a convolution. So normally, you would say something like tf_get variable. You'd give this variable a name, a size, and possibly an initializer, but there are some default initializers, so you don't need to specify it every time. And then call an op on the variable. Right? In the core model of TensorFlow, the ops take inputs and produce outputs, but they never create variables. On the other hand, when you call a convolution layer or an embedding layer, you would assume that a variable will get created for you. You don't want to every time write like embeddings equals tf variable this. Convolution kernel 1 equals tf variable this. Convolution kernel layer 31 equals this. If you can do this by hand, but very quickly you'll be very tired and start losing track of these variables. So there are these things called scopes, where you can create variables that will be under the scope, and you can write Python functions. So this is an example of a function you can write that will, well, open a scope so that it doesn't conflict with other things, and then create a variable and call an op that uses this variable. So this is actually how word embeddings are implemented. You give it some words, which is an int32 tensor. You tell what's the maximum number of words and into what size vectors you want to embed them. You get the embedding variable, which is always vocab size by dense size, and you call the gather op, which is like matrix multiply but sparse. So it will look at this x and select these positions on the first dimensions. I don't know if who's worked with word embeddings? Okay, so you probably know the code. So word embeddings are quite a standard thing that if you want to make a neural network work on text, you have the words which are IDs in a vocabulary, But what you want is dense vectors so the network can do matrix multiplies and things like that. And the way you do it is you just create this large matrix, which is vocabulary size by some vector size. This is often something like 30,000. This is often something like 500 or 256. And then when your input comes, which is the x, you will select the rows from this matrix that correspond to these IDs. And you want to do this fast because this is a very large thing, possibly, and this is just a sparse subset. But that's here to illustrate how you can write a Python function that will maybe create a variable, call some ops, it can call a number of ops, and that's it. And now you can use this as if it were an op. So the terminology we actually use is, we call layers operations that create variables. So we reserve the name ops for things that don't create any new variable nodes. But maybe that's not important, it's just. And then when you have a bunch of these layers, you can build whole models. And this is actually a part of a true implementation of a ByteNet model. So if you have some set of layers, you just call them, like you can call one layer, another layer, a convolutional block. In the middle, you can call just basic ops, like concat of some tensor. And then you call another layer. So this is how a model code usually looks like. Just to give you, not to go into the details of these things, but when you write models, you try to write these small things separately so that the model becomes a more readable thing. And of course, you don't have to do it like that. So this is one way of writing models. Another way is to use Keras, which is also a very nice way. But another way is to use just the core TensorFlow and have, x1 equals tf variable, x2 equals tf, x37 equals tf variable, comment, that's the kernel for layer 17, second tower, and then put them all together, wrap them in a class for no clear reason, unluckily, the final way is the most common currently. So TensorFlow doesn't force you to do any of that, right? How you structure your models is entirely up to you. The only thing it forces you is the core model of ops and things. But it allows you to structure these things, and it also allows you to use Keras as another way of structuring them. And it's a very good idea to stick to some format like this. Because you might think that you have full control of your model. There are these 15 variables that you'll be using, and that's it. Because your model are just these layers. But 2 days later, you will add another layer to your model. You will add another weight. You will try to remove something. You will try to add a normalization somewhere. You will have a colleague who will tell you, but you need to try this new something. And 2 weeks later, you will not be able to go through your own model. Even though these things, they fit on a slide, compared to like software engineering before, these are tiny things. The TensorFlow libraries that are, they're Python programs with a few hundred, maybe a few thousand lines. So on the software engineering side, they fall on the tiny scale. But deep learning is a tricky business. You need to be very careful about every single parameter here. So it's a very good investment to organize these things from the start. And it can save you a lot of pain later. Okay, so now you've built your model graph, and now you want to run the network, and you come to the realization that you'll be running it for training, and then you'll want the same network to run for evaluation on a different data set, And then when you're finished, you'll want to run inference on this network, which will be quite similar but different because it will not have the ground truth to evaluate the loss. You will want the predictions. And also, then you realize that the evaluation actually needs a slightly different graph than the training. Because, for example, you have dropout in training, but you don't want dropout in evaluation. So what you realize, you'll need three methods: fit, evaluate, and predict. So this will train, this will evaluate, and this will give you predictions. And it turns out it would be nice to have an object that structures this, right? It's called the estimator in TensorFlow. So an estimator is an object to which you have to give two things: your input function, and this input function will get a parameter called mode, which can be fit or evaluate, and it will construct the input to your model. For example, if it's fit, then it might read from the training data set. If it's evaluate, it might read from the development data set. And the other thing is the model function. It will also get the mode parameter. And this model function, it takes inputs that are already tensors. They're already after the input fn. And what it produces is a training op, an eval op, but also a list of predictions, which are somehow not on this picture, for the predict function. So the model function can be used for training, because it gives you a train op, for evaluation, but also for just inference, for generating predictions from the model. Mm-hmm.
Sorry, so the model function is pure Python, nothing...
All of these functions are pure Python.
No, sorry, I mean, where is the definition of the network? So
in the model function.
In the model function.
So this is the network, while this is just to hook up data sets with your model. And it's separated because you don't want reading from disk to be part of your model, because later someone will come and want to just get predictions from the keyboard, and then you need different ops. So you don't want to make this like a hard-coded part of the graph. So that's how a lot of people write higher level or TensorFlow nowadays. It's not contrib anymore. It's just tf.estimator nowadays. So you say estimator, you give it a model function that's built with some model builder. It also takes things like output directory, where to save checkpoints, some config. So this is for distributed training, which machines should see which machines and so on, and there is a default one, but you need to give it the master machine. And then there is the experiment thing, which allows you to run training easier. Okay, so that's the thing, and you asked, how does the model fn looks? Well, it gets a features, which is a dictionary. It has string names like inputs, whatever, inputs and other inputs, some extracted features. The model can have many inputs, but it's a string index dictionary. It gets targets, which are the tensors it will predict, and this mode thing, which is infer, eval, or predict. And input fn, well, it needs to, it needs to provide these. So input fn takes no arguments, but it returns this features dictionary and the targets. And if it's an infer mode, it doesn't need to return the targets. So, okay. So that's it's not the core model, right? It's all Python, but it's how TensorFlow models are structured. And this, especially this estimator, is becoming more and more of a requirement, meaning it didn't exist in the earlier releases of TensorFlow, but a lot of the higher level libraries nowadays, they require you to construct an estimator. And the reason is that if you have something that does training for you, handles distributed machines, splits your model. Right, so TensorFlow is distributed in its core model. But now imagine you want to do distributed training. So you will take some data, and you have 20 machines, and you want to just make 20 batches of the data, run a training step on every machine, and get back the loss. How do you do this? In the core TensorFlow model, you need to write the ops for every of the 20 machines. Right? So the graph will be different every time, depending on your hardware configuration. That's not too pleasant. You need to somehow manually specify how to distribute it. When you have an estimator, you can just specify the model fn as a function that builds the graph one time, and some higher level library, that could manage distributed training, can take your estimator object, replicate it 20 times on your 20 available machines, and then hook it up to the inputs. So this allows people to build higher level distributed training methods.
If we have estimators, why we need experiment? I mean, what's the addition of the experiment on top of the estimator?
So estimator only gives you a single training step thing and a single eval step thing. Now experiment handles the actual running of it. So you want to, maybe run 100 steps of training, then evaluate, then
Determination policy.
yes. So there are these hooks that are also called monitors. Maybe you want to, if eval stops decreasing for 5 steps, then change the learning rate or run some other op. Yeah, it handles the training process, while estimator is really the model. Okay, so these are the, right, that's how it looks, and then there are high-level libraries, and I won't go much into it, but there is Keras, which is a great library to build your own models. There is Tensor to Tensor, which is a library I've been working with for a long time now. And they sit on top of everything I said, right? So you have estimators, you have experiments, they will build them. But in addition to that, well, you still need to get your data from somewhere, right? And the data usually needs to be pre-processed in some way. And then maybe you have a library of models and layers, so you need to put them somewhere. So for example, in Tensor to Tensor, you will have a problem class that has a lot of instances for different data sets. So if you want to train a translation model, you can just say, oh, there is a class that knows where to download it from, how to create a tokenizer to build a vocabulary, and how to pre-process stuff and make tensors out of it. And if you have an image, it will know, okay, this is where there is this Microsoft image data set, and I know that these are 3-channel PNG images stored in this way, and I'll download them and convert them into TF examples and put it there. And then it has models that can work on this problem. And so this model class will be used to create an estimator, which will then be passed to an experiment. So it's another layer on top of the many layers we've had already. But it's what allows you to say, like, okay, use this data set to train this model for translation or something like that. And whatever, that's maybe not important. And you can register things with annotators and add your own problems. Yeah.
So all the models inside Tensor to Tensor like transformer are meant to be used with an estimator, experiment.
Yes. And they are.
Okay.
So
I can use them on their own. with estimator, for example, for a custom
Yes,
behavior
yes,
or-
yes, yes, and that's actually what happens in the class. So everything is an instance of T2T model class, and what you implement is like this model body function, but the class provides an estimator.
For the class itself.
Maybe it's in somewhere else, but it should provide an estimator. And right, but it provides also a bunch of other things because the model body is like a single machine thing, and currently the estimator, like the experiment will not make the distributed version of the model. So the class actually has to know how many GPUs you have to make the multiple copies of the model to allow distributed training. And sometimes it's more complicated than that, because in some models you want to do distributed training but actually communicate across machines, and that's a technical problem. So the distributed part is sometimes quite tricky, but in many cases you don't need to worry. You just write, here is my single machine model, go train. Another thing that you normally need to worry is, say you have a translation problem, but you have a vocabulary of 8,000 things. Right? I've shown you before that there is an embedding layer. It creates a variable of size, vocab size by some dense size, right? So if this variable is created in your model, then your model will only work with a specific vocabulary size. You change your vocabulary size, you need a new model. Now that's not reasonable. We don't think about the vocabulary size as a property of the model, it's a property of the problem. Because you train a model for parsing, it's the same transformer model, except now you have 1,000 classes instead of 30,000. So what? Do I need to write a new model? Well, put it into the problem, and then you can hook things up.
But it's still true that once you've done the training, then the vocabulary is part of the model in a sense.
Yes, it's a variable. It lives in a checkpoint. There is no way around it. But it's abstracted away from the model code. And yeah, I mean, I think that's the overview of TensorFlow. So as you see, it's a multi-layer system and more of a whole ecosystem. So the core TensorFlow is one, but there are many targeted hardwares, and some don't support some ops and things like this. And then there is the general library with estimator and a number of higher level libraries. And some people just using the lower level core code. So yeah, so that's how it looks. And the question is, what would you like to know more about?
The relationship between Python and TensorFlow. Python is a language in which we express the graph.
Yes, graph and the session.
Run the session.
Yes, and you can run the graph from C. I think you can even construct it in C, but it will be very unpleasant. Because the gradient method is not, the function that computes the gradients is currently a Python method. So if you want automatic differentiation, you'll need to use Python. And you want automatic differentiation because.
Very general, actually. Why Python? I mean, I saw even in other projects that they are experiencing a lot of problem in multithreading, of course. Like they didn't realize earlier that the problem was the global lock of Python. So it's for simplicity, there's something more in the choice.
But what would be? I mean, Go. No, I mean the point is, well, you could write a new programming language, right? But that's not a like you could use Lua, like some other frameworks do. And then you'd have to rewrite your framework in Python 2 years later. I mean, the point is people use NumPy for data analysis. And people know NumPy, and it has evolved to be quite a reasonable interface. So the other point is you have a lot of these ops. What should they do? Should you make up your own things for every op that operates numerically on things? Then everyone would have to learn a new thing. So TensorFlow tried to follow NumPy with the ops. So in the way that they do broadcasting for adding, in the way the reshape works, and in the way the parameters are structured, they try to be as close to NumPy as possible. And well, since NumPy is a Python library, it seemed to make sense to just go with Python. And yeah, I mean, I think it helps people in many ways.
And you do all of your research and development in Google using TensorFlow. You do all of your research and development in Google using this.
Yes, I use Tensor to Tensor for all my research.
No, I mean, is there any other, for example, open source library apart from this one that you use, or is it the universal model in Google? Is it the universal model in Google, like everyone uses it for research and development in Google?
TensorFlow, yes. Some people use Keras on higher levels, some people use Tensor to Tensor, some people just write core TensorFlow code. So on that it differs. But everyone uses TensorFlow, and nowadays almost everyone uses Estimator as well. That's became standard. And on the higher level, there is a library called Slim that many people in machine perception use. It's a very fun library as well. And that's widely used. Yes, but it's all just on the higher level part. Until then, DeepMind has a higher level library called Sonnet, which they use. They have slight differences, but the nice part is they're all interoperable. So you can take model from here, add another TensorFlow op. I mean, they all built TensorFlow graphs in Python. And you can mostly mix and match.
There is a service, cloud service of Google for use TensorFlow and distribution.
Well, in a true Google fashion, there are already two. Yes, so there's CloudML and Cloud other thing, yes. So there's one service where you just give a TensorFlow graph, and it will run the experiment object, and it will run the training for you. And then there is the other thing where you actually get a virtual machine where you can so in this other thing, you just put files into the distributed file system and it runs your TensorFlow graph, but it's all managed.
And to rent some servers to make distributed.
Mm-hmm. Yes, that works. That works like quite recently. The other thing where you can just really have your own virtual machine, a bunch of them, and run whatever Python code together with your TensorFlow you want. Yeah, that's. But setting up distributed machines on your own can be annoying because you need to tell them which machine is where.
My question was, since experiment takes care of the training,
Mm-hmm.
but a big part of machine learning is tuning, and especially tuning hyperparameters. Is there any library that is of Contrib that is built in for hyperparameter tuning or this kind of operation which you need to do once you've completed your model?
Yes. So there is an object called hparams, tf.hparams, which is basically a dict where you specify your hyperparameters. Now, people started, but I think it has been moving on and off to make ranges because, so there is a service called AutoML, I think AutoML or Tune. No, they rename the internal tools when they put them on Google Cloud, and I never know. So there is an internal tool which is available under some name on Google Cloud, which allows you to specify a range for every of these hyperparameters, and it will and a tuning algorithm, which is either Bayesian or some random searchy thing, and it will tune it for you. And internally there is a range object, which unluckily they changed to some JSON file when they did the Google Cloud release. So I don't know exactly how this Google Cloud version of the tuning works. But yes, it's if you use the H params, it's quite easy to specify the range for any param and then put it on cloud and let it tune. To me, the biggest problem is that none of these tuning algorithms, at least for me, really works too well. So if you want to tune one parameter or three, they'll work fine. If you just set everything and tune your learning rate and whatever, and epsilon for Adam and something like that, you might be fine with that. But if you specify 20 parameters to want to tune, and unluckily there's often a lot of parameters, like decay schemes, and this learning rate is just one point, but you often need to decay it in some way, and yeah, like with a little bit more, all of these, both Bayesian and the more random searchy, they just start doing strange things, and they often have the tendency to hit the limits of the range rather than the middle, and yeah, so.
I had the same with scikit-learn, and it was pretty much the same. I used random search, but it didn't seem random at all. Like it had a very strange parameters, so very similar to each other.
Yes, it's I don't know, but I've tried it a few times, and I think it's getting better. There is a small team working on it, but I think it's simply a very difficult problem to make these things reasonable. And I think the thing they started enabling recently is transfer learning from other experiments. So they will record, you give the experiment some prefix, and they will record all experiments with this prefix. So maybe because you change your model a little bit, and then this tuner needs to start from zero, retune everything, and that's just not feasible. So I hope one day this will come, but another problem with the tuners is what I wanted to tune once. So there is a bunch of optimizers like Adam, Momentum, Adagrad, maybe pure SGD. Sometimes one works better, sometimes the other. And luckily, by default, they have incompatible learning rate ranges. So Adam, the learning rate is usually 100 times smaller, at least, than a pure SGD to work well. But if you give it to a hypertuner, it treats them as independent variables. There's, oh, I tried this, and the very small learning rate was very good. Let me try the same learning rate for SGD. That's why, for example, in Tensor to Tensor, many people ask on GitHub, why the hell did you rescale? The learning rate hyperparameter is up to scale, and somewhere inside the optimizer it's multiplied. And people say, oh, but I thought for Adam it must be much smaller. Yeah, it is much smaller because it's divided somewhere. And it's rescaled to give a chance to this hyperparameter tuner, but it's still not doing too well. So it's it has especially problem with these categorical variables. So if you tell it, well, tune me a learning rate and find an optimizer, then it annoyingly tries to find a learning rate that's good for all optimizers. And it's somehow, yeah. I really hope one day that they'll get there, but yeah.
Who's building stuff that is not ML with TensorFlow? I mean, in theory, you can do your homework with TensorFlow to TensorFlow, but who's actually using it for that stuff? If there's
I think there is a fair number of people doing that. So there are people who do physical simulations. They use it on like their distributed clusters. There, I don't know. I think the scientific community is a user nowadays. I don't know who else. It's,
Okay, just curious.
you know, we don't get any statistics. Like,
Which is really
so some people come and tell us, but there is no tracking. You can use TensorFlow for whatever you want, and mhm.
What do you think is the best application of TensorFlow?
The best.
That you have used, I mean, you have been
Most
using.
useful, no, not most useful, most effective. Which context TensorFlow can be really effective?
Oh, machine learning. It's of course. Of course, it's the yes. Hmm?
What about XLA? So that you also have parallel part of compiling the graph using accelerated library. You have some news about that. XLA accelerated.
Okay, so let me explain. As if we didn't have enough levels already in the talk, people started seeing that this graph, it would be nice before we put it on hardware to add one intermediate layer, like pre-compile it into another mathematical library, which is called accelerated linear algebra. So currently there are like two modes. You can just run the graph, or you can pre-compile it with XLA, and maybe it will run faster. And the reason is XLA has some, so it can fuse some operations, for example. So it can see, oh, there is a matmul, and after this there is a relu, so I don't need to save the result of this one. I can make one op that does these two at once. And so it's like a mid-level compiler. The problem with XLA is it requires, so TensorFlow has these tensors that flow on edges, but it doesn't force you to specify the shape of these tensors. So every tensor, when it actually flows, it has a shape. But when a tensor flows another time, this edge, it might have a different shape. For example, when you do language, when you do text, you might have a tensor of batch size by sentence length by some fixed depth. So it will have a size that maybe batch size is fixed, 32, let's say, by some unspecified size. So in a shape object, it will be none, by, say, 256. And then if you have a short sentence, the one size will be whatever, 20, and when it's a long sentence, it will be 40. But it's no problem for TensorFlow. It's the same graph. It's just when it loads things from the disk, it will flow with different shape. Now, XLA requires all shapes to be fixed. So it has its advantages when you compile for hardware, because maybe you can do some better things. Maybe you can optimize things and so on when you know the shape. The problem is, especially in text applications, you often don't know all the shapes. So there is the whole work in XLA to do just-in-time compilation. Every time there is a new thing that flows with a different shape, it will run a just-in-time compiler to compile a version of this graph for this shape. And it works very well. I mean, it runs, except you need to be careful about how many shapes you have, because if you have like 1,000 of them, it will have to compile 1,000 things, and the compilation is not always that fast. On the other hand, I mean, so it's a mid-layer that has been maturing, and the hardware people, they're extremely happy about knowing all the shapes, because they say, oh, when I know shapes, I can do some things. I can know whether this matmul will fit into my hardware unit, or whether I need to split it in half and do two matmuls actually on the hardware. So they're very insisting on knowing that. On the other hand, like researchers or people like me are very insisting on not having to specify these shapes. Because in the early days of TensorFlow, like for every sentence length, you had to make a separate graph. and that's very annoying. You need to maintain it in your Python code. It kind of works behind you. When you do inference, things start to be strange. So XLA is progressing. It's well, I think nowadays you can turn it on. It's quite non-buggy. It sometimes gives speed ups, and I'm not even sure if it's not turned on by default nowadays. It's not yet. It's so yeah, it's a great piece of work. I think for the new hardware things, this will bring really good improvements, I believe. But yeah, it's.
Yeah, I also have a question related to sequence-to-sequence model, because I see that from version 1 they came also an example tutorial for sequence-to-sequence, and then they have one kind of library, and then migrated outside the Tensor Flow there were another project sequence-to-sequence, and then there is another. So do you have an insight why the sequence-to-sequence is so controversial in that?
I don't think it's controversial.
Yeah, but also for me, it's controversial. If you try the different version API, there's an issue on the Tensor Flow is like, I don't know, like 1,000 comments, because people try to do the tutorial, and there were changes on the version of the API, and they were discussing.
Right, but so I'm okay. Let me make this disclosure. I wrote this tutorial. I also wrote parts of the other one. So the first sequence-to-sequence tutorial was written TensorFlow 0.5 or something like this. That was before there was a while op. So at that time, there was no way to build a loop into a TensorFlow graph, and there were no conditionals. Your graph had to be a feed-forward thing. So for every sentence length, you had to build a separate graph. And this was annoying, and it requires, but you wanted to use the same parameters, for example. You don't want to use a different set of variables for different sentence lengths. So it was kind of an early test of TensorFlow, even before it was released, whether we can actually do it, because translation was beginning to be an application, and we wanted to know whether in this new system we can write it. So we wrote it. And it launched, and it was okay, and then people looked at it. We said, okay, we'll need loops in the graph. And doing conditionals in this forward-backward execution model is already tricky. And doing loops is a nightmare. Because, well, when you have a loop in a data flow graph, suddenly there are things in your node that are there the first time, the second time, the third time. So you need to keep a list of them, but then you'll be back propagating, so you need to make sure that your gradients are computed from the right timestamp. Well, that's not yet so bad. The bad problem is, like, it's distributed, so your gradients are coming from a different machine, which needs to have synchronized timestamps. And it has send and receive nodes, which can very easily deadlock. Because, well, you know, in the graph you have a send, you have a receive. But the receive is actually waiting in the execution queue of the other machine. But it's waiting for what? Like, in a feed-forward graph, it's clear. It's waiting for this node to finish computing, and it will send something. But in a loop, maybe it's waiting for something that will never compute because it's on a branch that will not get executed, or something like this. So doing that took a long time to make this reasonably non-buggy, and we didn't update the tutorial with the dynamic version, which uses loops for a long time, and by the time there was the version with loops, we were already thinking about newer models. So we got distracted, and who will update the LSTMs? Well, guys, we're doing other things. But it finally got updated, right? Now there is the NMT tutorial, which has the dynamic. Yeah, there is it lives now in the NMT repo. And yes, and it works, but in the meantime, you know, a lot changed. At TensorFlow 0.5, there were no layers. There were there was no higher level API. Keras didn't have a TensorFlow backend. So people like things were written in a much lower level code, and it was not clear what the higher level code will look like. Nowadays, it's much clearer. So the question is, why should we maintain a TensorFlow tutorial with this when there are higher level libraries that will do it for you? And on the other hand, some things, so one problem with the translation is that inputs have different lengths. So you're reading them from disk, and sentences with different length come, but you want to build batches of sentences with the same length. Because when you're processing a batch, if one is longer, you need to pad with zeros and process it till the end. So there needs to be some bucketing, which requires you to either load things in memory and do it in Python and feed and fetch, which has its problems, or to have these queues that do bucketing, which at first were hard to do, and then they were finally done in Python at the same time as people decided that we don't want Python threads. So now they are redone in the dataset API, but they're not yet ready there. So, so it's like every part of this tutorial has been redone a number of times. And I think we're slowly getting it right, but it's, yes, things are changing. And like, you know, maintaining the old stuff is, we try to do a bit, but it's a much better thing to go to the newer things.
Is it possible, strange question, I know, but is it possible to build a biased deep neural network to see the robustness of a model and use stuff like this for statistics part?
To see the
biased neural network, putting priors in each weights and see how much the confidence interval is.
I mean, you can do it, but you'll need to construct these things on your own.
So it's possible also to simulate from random variables inside?
Yes. So there are nodes for all kind of random distributions, and they'll generate you random variables, and what you do with them is your. So one application for TensorFlow that's not deep learning is the probabilistic or stochastic neural network and programming. And there is this thing called Edward, which is like a language for Bayesian or stochastic programming. And it has a TensorFlow backend that yeah. So
I was wondering, in your experience, which are the pros and cons of using tensor to tensor in comparison with Keras?
They're a little parallel. So Keras is very nice if you're building like models with many towers and many layers and so on. But Keras does not give you gives you a little bit of a trainer. But for example, I don't think it will distribute the model for you. And it doesn't really give you data sets. I mean, it has MNIST, I think, but you cannot find a translation data set that it will actually download and hook up for you. So I think they're a little bit in parallel. Like, if you want to get data, you'll probably need to use tensor to tensor. But then the really nice thing about TensorFlow is that this is all interoperable. So you can make a Keras model, put it in tensor to tensor, and it will run, and it will train, and it will all be fine.
So it's quite easy to change framework, to move from one framework to another.
Yes, or take, you know, you can write model code in one framework and use a trainer from another.
Yeah.
So yes.
That's nice.
So that's all. That should all work.
So, regarding your previous talk, what kind of network is an attention model, if it is a network at all, or maybe I misunderstood?
It's a net, like a neural network. Yes.
Okay. How is it made, like internally?
How is it made?
How is it made? What kind of network is it? The attention model in particular?
It's a feed-forward network. With this special kind of layers that's called attention. They're computing with matrix multiply and softmax ops. but I'm not sure what you mean. What kind? What would be an example of a kind?
Kind like recurrent, convolutional.
Well, it's a new kind.
Forward.
It's an attention
something,
attention network. Yes.
Network. Okay. Just wondering.
It's yeah. It's hard to